Okay. Hi, everyone. My name's Natalie, and I'm a mechanical engineering graduate student at Caltech, working with Nadia Lapusta. Our work is funded by NSF and USGS, and we use numerical simulations to investigate the effect of fault heterogeneity on earthquake nucleation. Many large events on natural faults are preceded by smaller events that occur close in both space and time to the large event that follows, like you've seen already earlier today. These events are termed foreshocks, as you already know. And here are just some examples of trends that we can see in foreshock behavior, where, I'll use the clicker here, these two plots show the spatial clustering of foreshocks leading up to a main event, and this one over here shows the temporal clustering. Well, these trends are observed for some large, for foreshocks leading up to some large events on natural faults. The relationship between foreshocks and the slow nucleation process, as well as foreshocks and the larger event to follow, still remains an open question. Greg McClaskey and his former colleagues at USGS in Menlo Park conduct experiments on a laboratory scale fault. It's a meter scale fault. And these experiments can help to shed some light on this question. From their laboratory observations, they infer a nucleation process occurring on their fault, shown by this cartoon. Again, the clicker's, oh, there it is. Shown by this cartoon, where this nucleation process is progressing downwards, and this slow nucleation process is shown in blue. From their observations, they conclude that the foreshocks that they see are occurring at asperities or bumps on the fault surface. And then in terms of trying to think about modeling the physics that they see on their fault, they suggest that it'd be difficult to describe these foreshocks in the slow nucleation process purely by a rate and state model. Part of the reasoning for this is that this model would need to be able to handle two vastly different nucleation sizes. One is the nucleation size at the patches or the asperities, which could be up to 2 orders of magnitude smaller than the larger nucleation process. So how do these natural observations and laboratory observations fit into the context of our work? Here are some driving questions of our work. The first is, how does the behavior of our numerical models differ for different patch properties and different distributions of patches? And then how much can the presence of asperities, meaning fault heterogeneity, influence slow slip, the slow nucleation process? And of course, the question that everyone wants to answer is, what can foreshock sequences tell us about the larger event to follow? The goal in our work is to compare simulation results with observations, in this case laboratory observations, to identify the physical properties of the fault heterogeneity. This is via our simulations of slow nucleation process with potentially seismic patches occurring existing within that region, shown here qualitatively by a red box. Now, in setting up our rate and state model, we create a velocity weakening region. This is our seismogenic region, shown here outlined by a white box. And then we embed this seismogenic region with patches, shown here by these red circles. In this particular case, our patches are distributed as a grid because before we run the simulations, we don't know exactly where that larger scale nucleation process is going to occur. So we have forced that larger scale nucleation process to interact with these patches by essentially putting them everywhere. Our hypothesis is that asperities are able to host smaller seismic events because the nucleation size there is naturally smaller, where this equation here gives us a 3D estimate for a nucleation size, which is extended from the 2D version from Rubin and Ampuero. Now, to be consistent with our asperity model of foreshock sources, we can decrease this we can have a smaller nucleation size at these patches by having both a higher effective normal stress, sigma bar, over here, and also after these patches repeatedly slide past each other, they could become smoother over time, which would correspond to a decreased characteristic slip distance L. So both of these factors could contribute to a smaller nucleation size. So once we set up our distribution of patches and our local properties of our patches on our 2D fault, we embed this fault in a 3D elastic bulk. And then through fully dynamic calculations, the output of our simulations is essentially the slip distribution in space and evolution in time. This here is just a snapshot of example simulation results. This particular one is of slip velocity. And when the slip velocity on this color scale reaches seismic speeds on the order of 1 meter per second, shown by a bright yellow color. In this particular case, we'd have seismic speeds, the slip is reaching seismic speeds at a patch, so this could be a smaller event, potentially a foreshock. So now let's look at some sample simulation results. This is going to be a movie, but before I show it to you, I want to give you a few words of warning. So the first one is that this simulation, this snippet of the movie is actually from the middle of our results, meaning that we simulate earthquake sequences on faults in the long term, so over multiple loading cycles. So this one is actually, the snippet is after the fault has already ruptured a few times. Another thing to keep in mind when watching this is that our time step is variable, so it's actually inversely proportional to slip velocity. So when things are seismic, then the time step is really small so that we can resolve that action. And then when it's an interseismic period, the time step is larger. So that might kind of mess up your sense of timing when you're watching this video if you're not used to that variable time step. The last thing is that when we're watching this movie, we should focus our attention on this box up here. This is where the larger nucleation process the larger event is going to nucleate. So now as we watch the movie, we can see this red creeping front moving inward and interacting with these patches to produce smaller seismic events. It's a little hard to see, but the brighter red shows that how the post-seismic slip from rupture at one patch can interact with a neighboring patch, potentially triggering an event there. Eventually, the quickly slipping region will reach a critical size. It's happening up here. And if any of these smaller events were to be considered foreshocks, it would be these ones occurring in this region. Now we see it reaching a critical size and then rupturing the entire seismogenic region. Go forward. I don't know why it's not going to the next slide. Somewhere else? No. Do you guys make it go forward? What about this? There we go. Okay. So how can we compare the simulation results from different simulations, so situations where we have different patch properties? One way to do that is to look at the maximum slip rate on the fault over time. And these are 3 examples of that from 3 different simulations, so 3 different sets of patch properties. In this first case, we achieved the smaller nucleation size at the patches purely by decreasing the characteristic slip distance L, in this case by a factor of 10. Qualitatively here we see that we get many event attempts shown by these spikes in slip velocity, but that not many of these event attempts actually reach seismic speeds of about 1 meter per second. Then instead, if we go all the way over here to the right and create the smaller nucleation size purely by increasing the effective normal stress tenfold, we see that qualitatively we get very different results. We get far fewer event attempts. We only have a couple spikes here, but all of them are seismic. Then if instead we combine these effects, having a higher sigma bar and a lower L, we get some behavior that's somewhere in the middle. An interesting observation that we had in looking at these simulations is that we actually can get seismic events occurring on patches that are theoretically too small. So by that I mean that they're smaller than that nucleation size estimate that I showed you earlier. This only happens when at least the local compression, the local effective normal stress is increased. And this is actually in line with the theoretical predictions from McClaskey from the lab experiments. And we think that maybe part of what's contributing to this occurrence is that the stronger patches actually rupture differently. So how are we doing in trying to match the laboratory observations? Well, first off, we're trying to match the laboratory observations in with a variety of parameters. We want to match their small moment magnitudes, of course the source size, so the size of the patches, their stress drop, the moment rate function, and then how frequently these smaller events are occurring, all the while handling these 2 vastly different nucleation sizes. This table here shows the ranges of the laboratory results in the first column, and then the second column shows the results so far with our model. We can see that so far we are handling the larger scale nucleation size of about 1 meter, and also our stress drops are within their observed range. But in terms of the moment magnitudes, we're a little on the high side, and in terms of our patch sizes, we're also a little bit on the high side. And these results, these larger patch sizes match to the McClaskey and Kilgore 2013 paper, but then in 2014 they reported smaller source radii, so we still need to step down to match those. But so far we can say that the patches that match the laboratory observations the best are ones that have both the increased normal stress sigma bar and a lower characteristic slip distance L. This helps us in a few different ways. So the first one is that the significantly higher normal stress helps to decrease the foreshock occurrence frequency, as we saw on the last slide. We also, if we include some effect of decreasing L, then it helps us to keep that normal stress at a lower value because we have some assistance from a decreased L to have that smaller nucleation size. And then another thing that helps us in our quest is that we do have this observation of these subnucleation size patches. And so we can, again, that helps us to keep the stresses within more reasonable ranges. So based on our results so far, we have shown that we can indeed simulate a larger scale nucleation process that triggers these smaller events occurring within the nucleating region using a rate and state model. We've seen so far that these patches, these foreshock producing patches that match the laboratory the best are the ones that have these combined effects of sigma bar and L, and that we can get these patches to produce seismic events even when they're subnucleation sized. So in terms of future work, we would like to investigate the scaling of these smaller events occurring in a heterogeneous environment, and also the seismic radiation from these events to see if there's any characteristic signature that tells us about the fault heterogeneity. And then in terms of trying to match the laboratory observations more closely, we hope to see if we can reproduce their smallest moment magnitude, smallest patch sizes with still physically realistic parameters, so not having stresses that are so high that it's unreasonable. In terms of a more overall goal, we would love to be able to identify whether and how foreshocks affect the nucleation size, the duration of nucleation, and the location of the eventual larger event to follow. And then once we wrap up the sub-project relating to the laboratory observations, we would like to be able to simulate event sequences with foreshocks on natural faults. So with that, I'd like to thank you for your time, and I'd be happy to answer any of your questions.
We have time for questions. Yep, right here.
Are your disparities all the same? Are they the same stiffness, same size?
Yeah, so for a given...
Could you repeat the question?
Oh, sorry. Yeah, the question was if all of my asperities are the same. So for a given simulation, they are. That grid of asperities all have exactly the same properties, but for a different simulation, they would be different.
And why did you get
Any localization? You mean why would events occur at one patch, not the other, or? Well, yeah, that's true. Well, everything's the same in terms of the properties, but for example, the loading is coming in from the outside and moving inward, so the outer patches rupture first, for example. You can also see that in that movie, things aren't symmetric. So even though the patches are the same, we actually purposefully create something that's asymmetric because a perfectly symmetric results wouldn't have anything to do with natural events. So actually, I didn't discuss it, but in one corner, we start our simulations with a higher pre-stress to sort of kick that asymmetry. So we do things like that to try to make it asymmetric. So once that happens, then one patch is more likely to rupture than another.
all along the work we're doing from the class in my lab, we can now image the disparities.
Mm-hmm.
And it has to do with the stiffness of the disparities, which has to do with the size, which has to do with the normal stress. You don't get any kind of equal distribution. Then you can start to see localization from where there's fewer asperities, where the material is less stiff. And we're measuring down to -8.4, and we can actually see asperities on micron scale.
Yeah.
Sorry, can I? What's your question?
I was just commenting on the difference if it isn't uniform and it's more like.
Yeah, so I guess my response to that would be just because our simulations have patches that are all identical doesn't mean that we think that's actually what's happening. It's just this is our simple way to test, what patch properties could be seismic and which ones couldn't. So we believe that in the natural fault, there's a variety of patch sizes, patch properties, all of that, but only the ones that are ready to go will rupture. Only the ones that are ready. Yeah, I guess I don't have a better way of saying that, but the ones that match would be able to rupture. So this is a more proof of concept thing, but then of course in the real case it'd be a wide variety of distribution of patch properties.